I'm going to use that area problem to motivate the concept of the definite integral. Okay, we're going to actually compute or calculate the area under a parabola. The graph of the function of the parabola is x squared from 0 to 1. Okay. Temporarily, you remember the idea. We're going to compute a, the area under the parabola from 0 to 1, by integrating approximations of the tiny portions of partial values of a. The wording is a little bit long, but you are going to see the meaning very shortly. Okay. Okay, you look at the screen. I believe you can see it. All of us know the graph of the parabola. Okay, y equals x squared. The whole thing, you look at the mouse cursor, is something like that. But for the problem we are talking about, we only need the portion to the right of the origin. The origin is here. Okay, we're going to actually compute, so not to estimate. We're going to calculate, to estimate, actually to find the area under the graph of the parabola from 0 to 1, which is the area of the black region. The area of the black region. Okay. Should I show you the idea right now, or? Okay, the idea is the following. You watch the screen carefully. Okay. We're going to compute the area by doing the following thing. There's a animation. You watch the screen. Okay, I'm going to play the animation very shortly later, but the idea is the first thing we do is to use the sum of the areas of many rectangles to approximate the area of the shaded region. Can I call the shaded region a curved triangle? A curved triangle, right? You have three sides. That side. So you look at the mouse cursor. That side is a curved side. You have two straight sides. Okay, I'm going to call this thing, the shaded region, a curved triangle. Okay. Now we are going to use the concept of limit to actually compute the area of the curved triangle. Okay. Anybody knew the area of the curved triangle? Probably it's pretty famous. Anybody knew the value of the area of the curved triangle? Okay, if you did not know, it's fine. Now concentrate. I'm going to show you how to use the concept of limits to compute the area of the curved triangle. Okay, and then we are going to use the procedure to motivate the concept of the definite integral. Okay. Now follow me. Okay. So temporarily, you do not have to care too much about the name, the Riemann sum. At the right moment, I'm going to tell you the definition of Riemann sum. What we mean by Riemann sum. Now we jump to question 2a. Okay. In question 2a, the thing we'll do is to divide the interval. You see the function is defined on the interval from 0 to 1. So probably I can show you the diagram on the screen. We're trying to compute the area under the parabola from 0 to 1. Okay. And we treat the function as a function defined from 0 to 1. This point is 0. This point has x coordinate of 0. This point on the x-axis on the x-axis, has the coordinate of 1, so the function is treated as a function defined from 0 to 1. Okay. Now listen to me carefully. Okay. Again, the first thing we do is to subdivide the interval from 0 to 1 into 4 subintervals with equal width. I want to repeat. To approximate the area of the curved triangle, the first thing we do is to divide the interval from 0 to 1 into 4 subintervals of equal width. Okay. And then we try to get the partition points on the horizontal axis. We divide the interval into 4 subintervals of equal width. The partition points, now we are trying to figure out the partition points. That point, of course, it's 1/4, right? So that point is 1/2. For some reason, so later on we're going to generalize. For the reason of generalization, I want to write this point in terms of the number 2/4. And likewise, this point is 3/4, right? So this point is 4/4. It's just something like the following. You have an interval from 0 to 1. Okay. If I want you to divide the interval into 4 subintervals, what are the partition points? Of course, you have the first point is 1/4, the second point is 2/4, right? The third point is 3/4, the last point is 1. For some reason, I want to write 1 in terms of 4/4. Okay, 4/4. That's what I did. Okay, in 2a, we divide the interval into 4 subintervals. I said using regular partition. By regular partition, we mean of equal width. Or you can say we divide the interval from 0 to 1 into 4 subintervals of equal width. Okay. We have seen the partition points. Okay, we have seen the partition points: 0, 1/4, and 2/4, and so on, right? And by the way, I wanted to include the 2 endpoints, 0 and 1, as partition points as well. Okay, and it's kind of the standard notation. I'm going to use x0 to denote 0. I'm going to use x1 to denote 1/4. Okay, and so on. Of course, the last partition point is denoted using x4. Okay, it's essentially 1. If you look at the graph in here, this partition point is 0. The origin is actually x0. So this point is x1, that point is x2, that point is x3, that point is x4. So don't think I'm nagging. Everything is relevant to the general formula of the definition of the definite integral. Okay, so just try to remember the notations, and also the width of the subintervals. So because we have been using equal width, the width of the subintervals are all equal. The width of the subintervals are all 1/4, right? For the notations, I'm going to use the delta of x to denote the width of the interval. Okay. Now you know all the notations. Now you know the meanings of all the notations in 2a, right? I told you the meaning of regular partition, right? We figure out the partition points, and the width is denoted by delta of x. And by the way, so this thing is called delta. Okay, it's uppercase Greek letter delta. Okay. I said it's delta of x. Okay, now concentrate. After we divide the interval into 4 subintervals using a regular partition, and then the idea is to use, now listen to me carefully, the idea is to use the sum of the areas of four rectangles to approximate the area of the curved triangle. I'm going to repeat. Okay. The idea is to use the sum or the total of the areas of four rectangles to approximate the area of the curved triangle. Okay, now let's try to figure out the areas of the four rectangles. If you divide the interval into four subintervals, so correspondingly you have four rectangles, right? Okay. Okay. Give me a little moment. I have to change the color to something I can write on white. Okay. Let's concentrate on the first rectangle. You look at the mouse cursor. That's the rectangle I'm talking about. I could give you another letter, A, B, C, D, E, F. So can I call this point F? Okay, now let's concentrate on the rectangle OADF. OADF, actually the first rectangle. Okay. The width of the rectangle, I told you, is of course. Okay. Now we're trying to compute the area of the rectangle. Okay. The width of the rectangle is nothing but 1/4, right? I told you to use the notation like the delta of x to denote 1/4 to denote the width of the rectangle. Okay. Anybody want to tell me the height of the rectangle? The graph of the function is y equals x squared, and the height of the rectangle is actually the height of point D. The height of the point D. If x coordinate is 1/4, okay, I'm going to call this point x0. I'll call this point x1. x1 is actually 1/4, right? Yeah, 1/16 is right. It's actually the value of the function at 1/4. Harrison just told me. Okay, I think it's not hard to see that. Okay, x, you concentrate on point D. You concentrate on point D. Okay, so that makes sense. Y coordinate of point D is actually the height of the rectangle. This point D is on the curve. X coordinate of point D is 1/4. And then the y coordinate of point D, because the point is on the curve, so y coordinate of the point D is computed using 1/4 the whole thing squared. Harrison told me it's 1/16, right? So that's right, actually. But for some reason I want to denote the height of, I mean the y coordinate of point D, so which is the height of the rectangle, in terms of the value of the function at x1, actually at 1/4. I read that in terms of the value of the function at x1, so just because it's easier for me to generalize for some other functions. Okay, so the area of the first rectangle, is given by the width of delta of x, and then times the height. The height is the value of the function at x1, okay, and then times the width. Again, the underlined is the height of the rectangle, and the double underlined, so delta of x, is the width of the rectangle. Actually, suppose you want to compute, so the value is computed using the value of the function at 1/4 at x1, the whole thing squared, and then times 1/4, right? Okay, so later on I'm going to use that form, you look at the mouse cursor, to generalize the area of the rectangle. So later on when we do calculation, it's computed and something like that. Okay. Anybody want to tell me the area of the second rectangle? I mean the area of ABCC. you look at this one. Okay, the area is ABCE. You could try to tell me the answer in two ways. One way is to use the general formula. The other way you could tell me the answer. So temporarily I'm going to label that using 1 to mean the area of the first rectangle. Okay. Now I'm looking for 2, the area of the second rectangle. So of course the width is the same. So anybody want to tell me the height of the second rectangle? The height, please. The height is actually the y coordinate upon the C. So that makes sense? You look at the mouse cursor. The triangle ABCE is the second rectangle. Okay, the height of the second rectangle is actually the y coordinate of point C. You know x coordinate upon the C is 2/4, and then you can figure out. So because the point is on the graph, for the same reason you can get the height of point C, or the y coordinate of C. Okay. If you use x2 to denote 2/4, I think the area of the second rectangle is represented using the value of the function at x2, so which is the y coordinate of C, right? And then times delta of x. If you really want to compute that in terms of the numbers, so this number is going to be the value of the function at x2 is 2/4 the whole thing squared, right? Again, if you know x coordinate of point C is 2/4, and then y coordinate of point C is computed using 2/4 the whole thing squared. So because the point is on the curve, right? Any point on the curve satisfies the equation of the curve. So that makes sense. And then of course the width of the second rectangle is actually 1/4, because the width of all the rectangles is equal to 1/4. So do you want me to repeat the same thing for triangle number 3? For triangle number 3 you are going to get, I think you have seen the pattern already. Okay. In terms of x1, x2, x3, and so delta of x is computed using the value of the function at x3. I think you have seen the pattern already. Okay, and then times the width of the rectangle, so delta of x, if you want to compute, it's computed using 3/4 the whole thing squared, and then times 1/4. 3/4 the whole thing squared is the height, and the 1/4 is the width. I will call that rectangle 1, rectangle 2. So maybe more precisely, the area of rectangle 1, the area of rectangle 2, the area of rectangle 3, the area of rectangle 4. Okay. One more. Okay. The fourth rectangle is computed. The area of the fourth rectangle is computed using the value of the function at x4, which is actually the value of the function at 4/4 or 1, and then times delta of x. Okay, and then 4/4 the whole thing squared, and then times 1/4. Okay. So we have seen the areas of the 4 rectangles, right? I want to repeat the idea. If we divide the interval from 0 to 1 into 4 sub-intervals, and then we're going to approximate the area of the curved triangle using the total of the areas of the 4 rectangles. On this slide, you have a small graph of the function and all the rectangles and stuff, right? Okay, I want you to understand this. A is the area of the curved triangle. the area of the curved triangle. Okay, I did not show you the area of the curved triangle on this slide, but if you look at that, it means the area of the black region. Okay. Now we are going to approximate the area of A using the total, the sum of the areas of the 4 rectangles. Okay. I think I told you before, the first term is actually the area of the first rectangle, right? So which is that, and the second term is the area of the second rectangle, so which is the second term in here, right? And likewise, I think you'll see what's going on. You look at this line. Any questions about that? The point is we are going to use the total of the areas of the 4 rectangles to approximate the area of the curved triangle, the area of the black region. Okay. So any questions about this? I hope so. This one is not too hard to understand. Okay. Now something new. I want to show you summation notation. So later on we are going to generalize this line. Okay. Before that, I want to introduce the summation notation. The summation notation is kind of this. It's called sigma. Sigma. It means the sum, the total of many terms. You listen to me. The meaning is you just remember one thing. Okay. You just remember one thing. I'm trying to say, to understand the meaning of the summation notation, you just remember one thing. Okay. In the summation notation, I is called the index. You see the little I is called the index. You just remember one thing in order to understand the summation notation. Each value of I will determine a particular term. This notation means you let I run from 1 to 4. So altogether you have 4 terms. Okay. So I value can be 1, I value can be 2, I value can be 3, I value can be 4. Okay. Altogether it's the sum of 4 terms. And then you remember each value of I will determine a particular term. Okay. Okay. Now for instance, if you set I value to be 1, and then wherever you see I in the term, you replace I with 1. Okay. I value of 1 will determine. Do you see I value of 1 will determine that term? When I value is 1, xi becomes x1. So I value of 1 will determine the first term. And likewise, I value of 2 will determine the second term. I value of 3 will determine the third term. I value of 4 will determine the fourth term. Okay. And likewise, the sum of these 4 terms can also be denoted using can also be represented using a summation notation. The same story. I value of 1 will determine wherever you see I, you replace I with 1. I value of 1 will determine 1 squared over 4 squared and then times 1/4. Okay, will give you the first term. So that makes sense. And the value of 2 will give you the second term, and so on. In the future, it's okay to use the summation notation if you feel comfortable, or alternatively, if you do not feel okay, it's also possible to try to write out all the terms, or give the pattern of all the terms. Very shortly, you're going to see it. Okay. But the bottom line, the key idea is we're going to approximate A, the area of the curved triangle, using the total or the sum of the areas of 4 rectangles in this particular case. Okay. Can I move on? I did this one in very detail. Okay, but we're going to generalize this. Now instead of using 4, I'm going to replace 4 with n. Okay, I'm going to replace 4 with n. with any, so by that we mean n can be 2, can be 3, can be 5, can be 4, can be 10,000, can be 100, can be 1 million, 10 millions, and n can be any finite number. Now we're going to generalize this formula, how to approximate the area of the curved triangle. We're going to generalize that. Okay. I guess I can show you the thing on the PDF. Okay. And by the way, this sum is actually called a Riemann sum. I'm going to introduce the term later. Okay. How we define the Riemann sum? This is a particular case of the Riemann sum for n value of 4, using regular partition and right endpoint. Why do I say right endpoint? For each small rectangle, I was trying to use the value of the function at the right endpoint as a height. The first rectangle, the height is given by x1, right? For the second rectangle, the height is given by the value of the function at x2, and likewise for the third one, for the third rectangle, the height is given by the value of the function at x3. I was using the right endpoint. You are going to get familiar with the terms, so but now concentrate on the idea. Okay. Now we are going to generalize. Of course, using four subintervals, the estimation is too bad, right? You see, using 4 subintervals, there are many gaps. Okay. So probably I can play the animation again. Okay. Actually, we are going to do the following. Now watch the screen. To make the estimations better, we are going to, so what do? We are going to increase the number of subintervals so that we can make the estimation better. The larger the value of n, the better the estimate. Eventually, the actual area of the curved triangle is going to be computed by taking the limit of the total or the sum of the areas of many rectangles as n approaches infinity. Okay, you see the idea already. Can I play this again? It's kind of interesting. Alright, that's the whole idea. Actually, that will show you how the definite integral is defined. So the answer to the definite integral of x squared from 0 to 1 is going to be the area of the black region, the curved triangle. We're going to see that very shortly. We're going to compute that very shortly. Okay. Now we're going to generalize. Okay. Instead of using n value of 4, you watch. Okay. Instead of using n value of 4, we are going to generalize to any n value. Okay. To form the Riemann sum, again, I'm going to make more comments on Riemann sum. Okay. We're going to use a Riemann sum to approximate the area of A, the value of A, which is the area of the curved triangle. Okay. So what we do is the same thing. We divide the interval into n subintervals. Again, n value is not necessarily to be 4. N can be 5, n can be 10, n can be 10,000, n can be 1 million, right? The larger the value of n, the better the estimate. I believe you can figure out the partition points. If you divide the interval from 0 to 1 into n subintervals, we still call 0 x0, okay, one of the partition points, and then you can see the next partition point is 1 over n. The one after that is 2 over n. The last one should be n over n. Anybody want to tell me how many partition points altogether should be in here? if we divide the interval into 4 subintervals, how many partition points altogether? If we divide the interval from 0 to 1 into 4 subintervals, we have 5 partition points. Okay. And for the general case, if we divide the interval from 0 to 1 into n subintervals, you have n plus 1 partition points. And the width of each subinterval is 1 over n. For the 4 subintervals, I can let you see this, the diagram, how to approximate the area of the curved triangle using the total of the areas of four rectangles. But for n, it's hard. Okay, but it's easy to generalize from the case when n value is 4. So do you see the pattern already? You just imagine n value is 4. You have that form, right? Altogether, you should have n terms. Of course, you have to use some notations to denote dot dot dot. Okay, that's the first term. The second term, this term is the last term, term n. Okay, in between there are many terms depending on the value of n. Okay, the standard notation, as long as you can see the pattern, you can use the dot 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 notation to indicate there are many terms in between. The rule of thumb, if you use the dot 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 notation, is write the first term, write the second term, and anything in between you use dot dot dot. There should be a plus sign in here. Sorry. There should be a plus sign in here. Okay, and then you write the last term. Again, write the first term, the second term, and the last term at least. Okay. I think you can also see the pattern in here. If you look at here, okay. Wherever you see 4, you just replace 4 with n. So do you see the pattern already? I'll try to zoom out a little bit so that you can see the two lines. So try to compare the two lines. Okay. That's the case when n value is 4. That's the case when n value is n. Okay. Wherever you see 4 in here, you replace 4 with n. You have the general case. Okay. Any questions about this? So temporarily very shortly, I'm going to make more comments on the last term. So actually, I can make more comments right now. Okay. Okay. Now, in this representation, altogether you have n terms. That's term 1, term 2, up to term n, right? You see, you have a common factor. In every term, you have n squared on denominator. You also have 1 over n. You have another n on denominator as well. So on denominator, you have common factor of n cubed. After taking n cubed out of all the terms, you see what's remaining. So do you see you have 1 squared remaining in the first term? You have 2 squared remaining in the second term. Likely you have n squared remaining in the last term. Okay. It's dot line. So this is dot line. Okay. And likewise, using the summation notation, if you do not like the dot 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 notation, so because we do not have too much time to talk about the definition of the definite integrals, okay, it's okay to use everything to represent everything using the dot 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 notation. But try to get used to the summation notation. I told you, so just remember one thing, okay? Each value of I determines a particular term. Now, for instance, for this notation, altogether you have n terms, right? The I value of 1 will determine that term. I value of 2 will determine that term. Okay. watch the mouse cursor. And likewise, each value of I will determine one particular term. And likewise, these two forms can also be represented using the summation notation. All right. Now the term Riemann sum. We're going to use Rn to denote the sum of all these terms. If you use the dot 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 notation, this part is called Rn. Okay. You look at the mouse cursor. F of x1 times delta of x. The first term is that, and then altogether you have n terms. The sum of all these terms is called a Riemann sum. A Riemann sum. I believe Riemann is a German name. More precisely, we say this is the Riemann sum using regular partition and right endpoint. By regular partition, again, we mean to divide the interval into unsub intervals of equal width. Okay. By right endpoint, you just imagine the geometric meaning. Actually, in each term, these are the values of the function at the right endpoint of the subintervals. I'm going to copy this part to the PowerPoint slide, and then I will make more comments now. Okay, now the big idea. The big idea. Now listen to me carefully. Now I'm going to talk about a big idea. Rn is the Riemann sum. Rn is the Riemann sum. Geometrically, no matter how large the value of n, we have seen a particular case when n value is 4. So geometrically, the meaning of Rn is actually the sum of the areas of many rectangles. Rn, I want to repeat, Rn is geometrically, it means the sum of the areas of many, actually of n rectangles. We can use this Rn to approximate A. A is the area of the curved triangle we want to compute. Actually, this A can be, no matter how large the value of n, A is actually approximated by the value of Rn. Okay. So give me one little moment. I will show you this thing again, and I'm going to make some more comments. Okay. Okay, I believe you can see this table. Okay, you can see this table. When n value is 2, I think we're talking about the third column. Okay, the values we're using are circumscribed, so rectangles. Now concentrate on the third column. Okay, on the third column, if we have n value of 2, the approximation, the estimate of the areas of the curved triangle is given by that value. Okay, if n value is 4, you have that value. Okay. If n value is 8, you have that value. We mentioned before, the larger the value of n, the better the estimate. If we use n value of 512, and then the approximation or the estimate of the area of the curved triangle is that. If we use a larger value, if we double that number, and then the corresponding sum of the areas of the rectangle is that number. Actually, all these values are particular values of Rn. This is the particular value when n is 2. The second line is the particular value when n is 4. The last value is the particular value when n value is 10, 10, 10, 24. Okay. That's a nice number in computer science, right? Okay, now you look at the screen. We can use Rn to approximate the actual value of A, the area of the curved triangle. Okay, A is the area of the curved triangle, so something like this is the area under the parabola of y equals x squared when x is from 0 to 1. Okay, and on the right hand side you have Rn. On the right hand side you have Rn. Rn is the sum of the areas of many rectangles. If I want to make the two things equal, anybody want to tell me a key term, a name, a term, a concept we have seen before? Can I try to rephrase the question? So what is the relations between these two things? I'm looking for a term. I'm looking for an operation. So something's missing here. So what's the question mark? So please. I believe you can guess the answer even. Okay. The larger when n is 512 is 0.33. When n is 1024 is 0.333. I believe you can guess. This line are getting this column. The numbers in this column are getting closer and closer to 1/3, because 1/3 is 0.3333. So thank you. So the limit. Okay, the limit. Okay. The thing I'm missing is the limit. So that makes sense. If you see that, then you got the whole idea. The limit of what? The limit as what? Approaches what? We just mentioned that the larger the value of n, the better the estimate. If we take the limit as n approaches infinity, right? If we take the limit as n approaches infinity, I was trying to write n in here. And then the limit of the Riemann sum as n approaches infinity is going to be the actual value of A. As you have seen on, can I play this again? The estimation is saying that, right? Now you have n value of 4, n value of 10, n value of many. Okay. When n approaches infinity, the limit of the Riemann sum, which means the limit of the sum of the areas of many rectangles, is going to be the actual area of the curved triangle, which is the area of the area under the graph of the function y equals x squared from 0 to 1. Actually, I believe now you can imagine. Okay, I'm going to make more comments. Actually, that's why I was trying to use that form. This form can be applied to any function, not only for the function y equals x squared. For any function, we can do the same thing. I'm trying to say for any function, I think I have another estimation here. For any function, did I use this one? For any function, we can do the same thing. So can you see the graph? Now you imagine that's not sine, that's any function. Actually, for any function, I'm trying to say for any function, it's possible to form the Riemann sum using the same way. Okay, and then if the function is positive, so geometrically it's an estimate of the area under the graph of the function, okay, when x is from some number a to some number b. Okay, I'm trying to say the Riemann sum can be formed for any function on any interval. Okay, and then it's also possible to take the limit of Riemann sum. Now the definition. Okay, now concentrate. The new definition. The limit of the Riemann sum on the next slide is actually the definite integral of a function from a to b. Now we look at the definition in some details. After that, I'm going to work on question 5 in real time. Okay. You look at item number 4. In item number 4, we can define the meaning of the definite integral of a function from a to b. Now concentrate. Okay. You do the same thing. The first thing you do is to divide the interval into unsub intervals using regular partition. By regular partition, we mean the subintervals are equal in width. And by the way, the following is going to work if the function is continuous. That's an important condition. Okay. I want to repeat. The following will always work when the function is continuous. If it's not continuous, you have to do a math major to see more complicated cases. But we stick on the case when the function is continuous. Okay. We divide the interval into unsub intervals using regular partition, and it's, I said earlier, it's always possible to form the Riemann sum the same way. We stick on using regular partition and the right-hand part. Okay. And then the definite integral of the function is defined as the limit of the Riemann sum. This is the definition of the definite integral. Okay. Again, geometrically, if the function is positive, so very shortly I will mention the geometric meaning of the definite integral. Okay. Geometrically, if the function is positive, then geometrically the definite integral, it means the area under the graph of the function when x is from a to b is comparable to the case when you have the area of a curved triangle. Okay. I know you need to do some questions before you can fully understand what's going on. Okay. But I will show you in real time how to evaluate the definite integral, okay, of that. I will rewrite the whole solution one more time, okay, so that you can see what to do again. So this time I'm going to give you some better wording. Okay. The first thing you do is to divide the interval from 0 to 1 into unsub intervals. With the regular partition. Then identify the partition points and the width of the subintervals. The partition points are x0 equals 0, right? And x1 equals 1 over n. And also dot dot dot. Of course, there are many partition points. I will give you the second last one and the last one. And x minus 1 equals n minus 1 over n. The last one should be xn equals n over n, right? So which is just 1, right? Figure out all the partition points, and also figure out the width of the subinterval. Okay? And the width of the subinterval is denoted by So delta of x, okay, so which is 1 over n, right? That is the first step with the proper wording. So second step, we form a Riemann sum. From the Riemann sum, with a regular partition and the red endpoints. So this time I'm just repeating what I did earlier. So this time I'm going to use the summation notation, okay, instead of using the dot 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 notation. So Rn in terms of the summation notation is the sum, the general form, okay, I from 1 to n. If you look at the handout, it's actually here, so you just copy this, okay. The value of the function at xi, and then times, so delta of x, right? For the particular function, it's the sum of n terms with the index running from 1 to n. The function is x squared, so the value of the function at xi, in this particular case, xi is I over n, right? So you have I over n, the whole thing squared, and then times 1 over n, which is the sum I from 1 to n, I squared over n squared, and then times 1 over n, okay. And then you can leave out the constant factor of 1 over n cubed out of the summation notation, out of all the terms. You have 1 over n cubed, the sum of, you just have I squared, I from 1 to n. I really hope you can compare the two notations, and then I hope you can see what's going on. I told you two ways. One way is to use the dot 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 notation. The other way is to use the summation notation. Okay. Actually, it's okay to use either way, as whichever way is comfortable with you. Okay. All right. So we got the Riemann sum. Still on step 2, whichever form you want to use, we are going to write the Riemann sum in some closed form. Okay, kind of say in closed form. There's a formula telling you. Actually, the formula I'm going to tell you is going to be on the final. I'm trying to say, if on the final I have a question like that, I will give you the formula. Okay. The formula I want you to know is still on step 2. Okay. The formula for computing 1 squared and then plus 2 squared and then plus up to n squared. There's a closed form to compute the sum of the squares of the first n positive whole numbers. Okay. Remember the formula. Okay. The formula is actually you do not have to memorize. Okay. Do I remember this formula? I think I do. Okay. On denominator you have 6. On numerator you have n times n plus 1, and then times 2n plus 1. I'm not sure you have seen the formula before, but if you haven't, try to know the meaning of the formula. If you want to use the summation notation, actually the meaning of this, using the summation notation, the sum of 1 squared plus 2 squared plus up to n squared can be written as the sum of I squared with I running from 1 to n. Again, each value of I will give you a particular term. If you know this formula, and then we're ready to compute the limit. So before that, so how about we still try to write Rn in some closed form? I'm going to copy Rn from here. Okay. According to here, Rn is computed using. I'm going to use the last form. Okay. Still, I'm going to write in two forms using the dot 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 notation. You have 1 over n cubed, I believe. You have 1 squared plus 2 squared up to n squared, right? Equals 1 over n cubed. If you want to use the summation notation, I'm going to put that in brackets. Okay, 1 over n cubed, the sum of I squared, I running from 1 to n. Either way is okay. Okay. One way is to use the dot 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 notation. The other way is to use the summation notation. Okay. Now we apply the formula I just told you in here. It equals 1 over n cubed, and then the sum of the total of 1 squared, so plus 2 squared up to n squared. I'm going to replace that with 6. On the numerator you have n times n plus 1, and you have 2n plus 1. Okay, this is the Riemann sum. Alright, so do you see the Riemann sum is in a nice closed form? So we're at step 2. Okay. In step 2, we actually computed the Riemann sum in terms of a rational function of n. Finally, the definite integral using this notation from 0 to 1, the definite integral of x squared is actually defined as the limit. You look at the definition I just commented. It's here. The definite integral of a function, in that particular case the function x squared, from a to b, in that particular case from 0 to 1, is defined as the limit of the Riemann sum. We take the limit of the Riemann sum as n approaches infinity. Okay, the limit of the Riemann sum. Do I have enough space to complete this question in here? So probably I have. I'm going to write a tiny bit smaller. Okay, you take the limit of the Riemann sum as n goes to infinity. I'm going to copy the Riemann sum. Okay, copy the Riemann sum. On denominator you have 6n cubed. On the numerator you have n times n plus 1, and then times 2n plus 1. You cancel out n from the numerator and the denominator, so n cubed will become n squared, right? I think you see what's going on. Equals the limit as n approaches infinity. On denominator you have 6n squared. On the numerator you multiply out the numerator. So what that, please multiply out the numerator. I think you have 2n squared, and then plus how many n's altogether? You have 1n and then plus 2n, and I believe you have 3n, and then you have plus 1. I think not a long time ago you did the questions like evaluating the limits at infinity. Anybody want to tell me how can we proceed? we take the limit of kind of a polynomial, a quotient of two polynomials as n approaches infinity. Numerator is a polynomial of degree 2, denominator is a polynomial of degree 2. Okay. The trick we mentioned before is to divide the numerator and the denominator by what? By n squared. On denominator you have I'm running out of space a little bit. Okay, so catch up one step. You divide the numerator and the denominator by by n squared. Okay, on denominator you have 6, right? On numerator you have 2, and then plus 3 over n, and then plus 1 over n squared. Anybody want more details on that, or can you recall the technique? You divide the numerator and the denominator by n squared. You have that. That's a trick we use to evaluate the quotient of two polynomials, right? Anybody want to tell me the final answer? As n approaches infinity, the limit of the second term on the numerator is 0. The limit of the third term on the numerator is 0. The limit of the constant of 2 is the constant of 2 on numerator. Okay. The limit as n goes to infinity, the limit of the constant of 6 on denominator is also 6. So the final answer is 2 over 6, so which is the same as 1/3. Okay. Okay. So 1/3 is the answer to the definite integral. The full name is, we say the full name of that is the definite integral of the function x squared from 0 to 1. The answer to a definite integral is a number. Geometrically is the area under the graph of the integrand when x is from 0 to 1. That's how I motivated the concept of the definite integral. So actually, originally we were looking for the area under the graph of the function y equals x squared when x is from 0 to 1, right? This area is, according to the calculation, this area is 1/3. The area of the shaded region on the screen is equal to 1/3. I think we have been using the second column. You see, we mentioned earlier, as n gets larger and larger, these are the estimations of the values of the area of the curved triangle. Okay, these values are getting closer and closer to 1/3. I think you have seen that. 1/3 equivalent is 0.33333, right? Infinitely repeating decimals. Okay, now you know the area of that is 1/3. Okay. Using this, we have also seen the definition of the definite integral.